we step through things here, but I'd like to welcome everyone today to today's technical webinar for FREEDM. My name is Ken Delaney, and I'm the Director of Industry and Innovation at FREEDM. For those of you who don't know, we are a power systems and power electronics research center headquartered at NC State University. Our research projects span renewable energy integration, electric vehicle technologies, control techniques, microgrids, applications of wide bandgap semiconductors, and traditional power systems analysis. We have extensive lab capabilities, including multiple simulation labs for hardware and loop development, an electronics packaging lab, and a high bay space for evaluating medium voltage applications up to 15 kV AC input. Together with our industry partners like ABB, Duke Energy, and New York Power Authority, we are leading the electrification revolution. So hopefully everyone is familiar with Zoom. We have disabled audio and video for all participants as they join, and we ask that you use the chat feature to ask questions. Just hover your mouse over the Zoom window and the button should appear at the bottom of that window. Click chat, type your question, and we'll answer as many as we can during the presentation. Note that this webinar is being recorded. Hopefully Ms. Kalal figured out how to hit record, or remembered to hit record. And we'll be posting this to the YouTube channel for the Department of Electrical and Computer Engineering at NC State. Today's presenters are Dr. Reza Tavakoli and Dr. Željko Pantić, and we'll be learning a lot about wireless power transfer. So I'm going to turn things over to Dr. Tavakoli.
Hello, everybody, and welcome to our technical webinar today. Here is the outline of our presentation today, and I will first start with a brief introduction about myself, and then I will continue about the WPT presentation. As Ken mentioned, my name is Reza Tavakoli. After receiving my bachelor and master degrees in electrical engineering in 2011 and 2014, I joined Utah State University as a PhD student. From 2015 to 2020, I worked at Select Research Center as a graduate researcher. Mainly there I worked on wireless charging system. The photo that you see on this slide has been taken in 2016 Select Showcase, where we showed a 25 kilowatt WPT system that was charging an electric bus in motion. You see the electric bus behind us in this photo. I continued my research there, focusing on wireless charging for other applications like electric wheelchairs and then passenger vehicles, and I designed several misalignment estimation systems. Since February 2020, I joined NC State University as a postdoctoral researcher. Currently, I work at FREEDM System Center with Dr. Željko Pantić, where we are continuing our research on high-frequency WPT systems. So that's enough about me. Let's dive into the WPT. Wireless power transfer is not new. Nikola Tesla published a paper in 1898 discussing the idea. And on the right-hand side, you see a photo of a paper published in 1921 when the author showed wireless power transfer with two coils having 1 foot separation. WPT is based on fundamental electromagnetic equations, Ampere's law, and Faraday's law. It has found many applications in electric vehicles, automated guided vehicles, and personal transportation like electric scooters. The main focus of this presentation today is regarding these applications. However, there are other applications like wireless power transfer for bioimplants, charging robots, charging cell phones, or energy harvesting for radio frequency circuits. WPT is basically using two methods. One is inductive and the other is capacitive. In inductive charging, we work with magnetic fields, while in capacitive charging, basically we work with electric field. However, we can have a hybrid, which is combination of inductive and capacitive. The other category is a stationary charger versus dynamic charger. In the stationary charger, we are doing we are charging the electric vehicle while the vehicle is parked, and we charge the battery. In dynamic charging, while the vehicle is moving, we transfer power to the moving vehicle. In this slide, I'm showing the basic structure of inductive wireless power transfer. We have our three-phase grid system after rectification and an optional buck converter to change the DC value of the voltage. We have a high frequency inverter that allows us to invert the DC voltage to a frequency from anywhere 20 kilohertz to 100 kilohertz. Then we have our compensation tank, which the main role of this compensation network is to compensate for the reactive power that the transmitter coil requires. It also helps us with the filtering the harmonics in the voltage or current. It can also help us to get a current source out of a voltage source. Then we have our transmitter coil. This transmitter coil is made of Litz wire. Litz wire helps us to reduce the proximity effect and the skin effect. We can also use ferrites to increase the mutual inductance. We can also use aluminum to help with the reducing the leakage field outside the transmitter pad. These components that I mentioned up to now, they are located at the road side and at the transmitter side. Then we'll have a air gap, and then we reach the secondary side that is located on the vehicle. We have a receiver pad, very similar in terms of having Litz wire, ferrite, and aluminum, but its dimension might be slightly smaller or bigger than the transmitter. Then we're going to have a compensation tank with similar role that we had at the transmitter side. And we have a power conditioner unit where it helps us to control the rate of charging of the battery. And then we reach to the EV battery. And this next section, I will talk about some frequently asked questions on WPT. The first question is, does wireless charging takes longer? Assuming that we have a 50 kilowatt wireless charger and a 50 kilowatt conductive charger, since the power transfer is the same, you're gonna charge your vehicle with the same rate during the same time. So WPT is no different than, wireless power is no different than conductive charge. Is it WPT good for the battery? The battery would not know if it's conductive charging or inductive charging. So in that sense, wireless charging is the same as conductive charging. However, if we assume that wireless charging or dynamic wireless charging allows us more frequently to charge our vehicle, then in that sense, it can be even good for the battery. Because in terms of more frequent charging of the battery, we don't allow the battery to be fully depleted. So in that sense, we can increase the battery lifetime. The other frequently asked question is WPT efficient? A misconception is that because we have an air gap in WPT, so it should be lossy. But it should be noted that the losses do not occur in the air gap. The losses in the WPT system occur on the same component that exists both in inductive charging versus conductive charging. So we are seeing now systems reporting with efficiency of 95%, efficiency of 97% in WPT. And these efficiencies are very similar to what you can get from a DC fast charger. So in terms of efficiency, we can get very similar performance. The other question is if WPT is safe. We need to pay attention to the fact that we are not going to energize a transmitter pad unless there is a vehicle on top and the vehicle has been acknowledged and authorized to be charged, and we are sure that that EV is compatible for receiving the power. A good analogy for that is like your kitchen microwave oven. Your microwave oven won't start until you close the lid. Here we won't energize the pad unless there is a vehicle on top. The other point is the operating frequency is standard says about 85 kilohertz, which is below the tissue heating based on the IEEE standard. However, we need to know that at 85 kilohertz, we would have some impact on the nervous system. So designers should pay attention to controlling the leakage field out of the, around the vehicle. The other question is about the impact on the grid. Let's think about a port facility. In the port facility, we have a lot of electric cargo handling trucks and forklifts. These are electric vehicles that need to be charged, and currently they are charged during the lunch break or during the evening when we have the peak load of the grid. But if we have EWPT and semi-stationary WPT in the port, we have the option to charge our vehicles more frequently, and that allows us to level the peak for the grid, and in that sense it can help the grid. The other factor is about compatibility. If we have seen we didn't see that any OEMs complaining about adding a new receiver pad under the car, so we are seeing that having a receiver pad being installed under the vehicles. We need to pay attention that either it is conductive charging for the vehicle or inductive charging for the vehicle. We always need two parts. One part goes on the ground, another part goes on the vehicle. So, and in terms of the price, the component that goes on the vehicle for DC fast charging would be very similar to the component you need for wireless charging. So in terms of the physical compatibility, WPT doesn't have any issue. But the other compatibility is about electromagnetic interference. There has not been any interference in terms of interference of WPT with the ADAS system, Advanced Driver Assistance System, in terms of automated vehicle. So we are sure that WPT would not interfere with that. And we haven't seen any interference with the power electronics in the electric vehicle. And we haven't seen any conductive or radiated emission due to WPT. One important factor is that now, do we have economic incentive to go toward WPT for electric vehicles? The most probably future of driving would be autonomous driving. And autonomous driving would need autonomous fueling. So right now you see currently we have vehicles with automated parking. If you have automated parking, then we can simply add automated charging and it would have a very huge market for that. But what we think the immediate market for WPT for electric vehicles first would be fleet, port facilities, trucks and buses, last mile delivery vehicles, and then passenger vehicles. A good example of electrification is Northern Europe, where electrification is happening right now. But you might ask that why we don't see commercialized dynamic wireless power transfer. Right now we have commercialized a stationary WPT system, but in terms of dynamic wireless power transfer, we haven't seen the commercialized one. One of the reasons is the higher cost, because for DWPT, we need to put the transmitter pads into a long portion of the road. It would require a lot of money. The second problem is about efficiency. People have used longer coils for dynamic wireless power transfer to transfer more energy. In that sense, the efficiency would be lower compared to compact coils used in static charge. The other problem is about autonomy and misalignment. Until we have full autonomous driving system, we always have misalignment between transmitter and receiver pads. And because we have misalignment between transmitter and receiver pad, the power transfer capability would drop, the efficiency would drop. And the last but not least would be the need for standardization. because there are several types of vehicles that they need to be charged from the same road. So they need to be interoperable. So we need a standardization here.
Hey, Reza, we do have a question from one of the attendees real quick, and it's related to dynamic wireless power charging. How do you select the Litz wire parameters, for example, for a 1 kilowatt system? And that may be a really long answer. I don't know if there's a short answer for that.
A short answer would be how much current you want to have in your coil, and probably based on the rated current that you have, you can select the AWG Litz wire that you need.
Okay, thank you.
Thank you. So with having these four problems with the dynamic wireless power transfer, I will explain about two projects that in those projects we try to address these first three problems: the cost, the efficiency, and the misalignment. These projects were sponsored by Toyota Motor North America. So here on the top side, we are showing the block diagram of a DWPT system. The research on DWPT system is mainly focused on the coil or pad design, on compensation topologies, and the power converters and control methods. Starting with the transmitter pad configuration, the initial topologies for DWPT, researchers were using elongated rails. These rails, anywhere from 10 meter to 25 meter, they were providing a stable power transfer. However, because we were energizing a very long portion of the road, the efficiency was low. We had a simple controller, but we had some safety issues as well here. The other option is to use lumped pad. These pads are very similar to the pads that we have for stationary charging. In terms of stationary charging, we have high efficiency, but because we have a lot more number of pads and each pad needs its own inverter, the cost would increase, the controller would be complicated, and the power that the vehicle would receive would be pulsating. In this project, we went with the compromise between these two options with elongated pad, anywhere from 1 to 3 meter, a compromise between these two options that I just mentioned. So we started with optimization of the elongated pad, and we selected rectangular pads and tried to optimize a dozen of important variables here, from the length, width of the length and the width of the coil, and all the parameters that are affecting the operation of the pad. We developed a optimization algorithm mainly based on particle swarm optimization, and we looked at two main functions. One was the cost of the system and the efficiency, and here the cost is the entire cost of the ground assembly, including the pad, Litz wire, ferrite, and aluminum, as well as the inverter cost and the compensation cost. And we normalize the cost per meter, so we have a better understanding about what's happening when we increase the length of the coil, not just the cost per pad. And we looked at the efficiency of the pad. The color bar on this scatter plot on the left-hand side shows the length of the different design, and each dot in this scatter plot is showing one unique design. And we can see that shorter pads with the pad length about 1 meter, here you can see blue ones are about 1 meter, are having higher efficiency, which was expected, but at the same time it has higher cost. If we select longer pads, which are about 3 meter, we have lower cost but lower efficiency. We can obviously see a Pareto front here, and designer needs to decide based on the desired cost and desired efficiency, select a design from this Pareto front. The other thing that we need to select here is what is the power drop we are allowing between two consecutive pads. As the pads are closer and closer to each other, the power drop between two pads, the power drop that the receiver would see would be reduced. what we decided in this project was that we want a seamless transition. So when the vehicle goes from one pad to the next pad, we don't see any drop between the pads, Then we wanted to have a fully sensorless operation. So the scheme that we picked was when the vehicle is well before a transmitter pad, we don't have any mutual inductance. In this case, we energize the transmitter coil with a low current. And because we have no mutual inductance, we cannot transfer any power. As the vehicle approaches this transmitter pad, we can see an increase in the mutual inductance. As the mutual inductance increases, we can transfer some power to the receiver. And that increase in the power transfer would be reflected on the DC link current, which is on the roadside. So the controller just samples this DC link current, and whenever it sees a change and reaches a threshold, it will increase the track coil energization current to the full current. And while the vehicle is on top, we can transfer full power. As the vehicle goes away from the transmitter pad, the mutual inductance would drop. And as the mutual inductance drop, power transfer capability would drop. And due to that, the DC link current would drop. When it goes below a threshold, we fully turn off the pad and we have a sensorless activation and deactivation of the pad by just looking at the DC link current, which is located at the transmitter side. As I mentioned before, we wanted to have a seamless transition between the pads. So here we are studying 2 pads, but it can be extended to any number of pads. When the vehicle reaches the first pad, we see similar performance as I explained in the previous slide. We energize the first pad as the vehicle reaches on top of the first pad. But here, the first pad, because he's transferring power, it will inform the red pad, this next pad, that a vehicle is coming. So the second pad is ready. And the moment that the DC link current for the first pad starts to drop, the controller energizes the second pad. So when the vehicle is in between 2 transmitter pads, both pads are energized and the transmitter coil current are controlled such that the summation of the power transfer would be constant. So vehicle does not see any drop in the power. As we reach over the second pad, we have enough mutual inductance, we fully turn off the first pad. Based on these 2 sensorless activation and the seamless transition, we designed a comprehensive controller which detects 3 critical time instants. These time instants are instant 1, 2, 3 that I'm showing here. Each pad has its own microcontroller, has its own inverter, and by just measuring the DC link current and controlling its inverter, it can do this sensorless activation and deactivation and the seamless transition that you see here. To show we implemented this algorithm on an experimental setup. We designed our transmitter pad for a 30 kilowatt system. 3 transmitter pads were manufactured and embedded in the road that you see on this left-hand side. We used a Toyota RAV4 vehicle and installed the receiver pad under the vehicle. We implemented our inverter, compensation tank, and controller boxes in an electric panel by the road. This test that we conducted was at 3.7 kilowatt. Later on, my colleagues at Utah State University went ahead and improved the power up to 30 kilowatt. On the left-hand side, you see the DC link current, inverter voltage, and inverter current at steady state. And on the right-hand side, you see the operation with 3 pads. And these pads are energized and de-energized such that we have a seamless transition in between, and each pad is only energized when the vehicle is on top. we tested the vehicle at different speed. And as you see on this left-hand side, we have the track current of the first coil, first with a low current. When the vehicle reaches here, we go to the full power. And as the vehicle is passing by controlling the track current, we transfer a constant power. And then as the DC link current is going down, we energize the second pad. We increased the vehicle speed up to 40 miles per hour. That was the maximum speed that we could achieve in our test track. We have more oscillation, but it should be noted that each pad is only energized about 100 milliseconds. And in this 100 milliseconds, we are able to fully energize and turn off each pad at the exact time. And you see the moment that DC link current here at the first pad is starting to drop, the second pad starts to increase, and for the third pad, and it can be extended to any number of transmitter pads. Here is a video of the test that we were doing in our test track. You see on this monitor that first the first track current is energized with a low current, and then the three pads in this test track are energized one after each other. The photo you see on the previous slide, it is the relevant test with that.
So Reza, before the slide, we did have a question. How far or how deep are the coils embedded in the roadway?
They are about 2 inches here. And I think that is like the, you want to have the minimum depth, but like, you cannot have less than 2 inches.
Okay. And then is there anything special you have to do to protect the coils from the backfill?
No, we didn't do anything about that.
Okay.
Other thing is about how fast are we energizing the pad, and we are going to that initial energization in 600 microseconds. 600 microseconds means that at 80 miles per hour, we only the vehicle only moves about 2 centimeters. It means that if the receiver pad is just 2 centimeters before the first pad, we have enough time to go through all these wireless power transfer. With this test, I will go to the next project we did, was considering misalignment estimation system. I explained before that as we have more misalignment in our system, the power transfer would drop, and as well as efficiency would drop. So we designed a system that helps us to estimate the lateral and vertical misalignment of the vehicle. On the right-hand side, you see the 3D view of the system structure. And what we are seeing here is we are using the same transmitter coils that were in charge of transferring power. We use the same transmitter pad to estimate misalignment. So we see the transmitter pads and the receiver pad here. They are in charge of transferring power. We installed 3 tiny sensing coils in front of the receiver pad. And then on the left-hand side, we see the EV bottom view, and where we are installing our sensing coils under the front bumper of the vehicle. And these sensing coils are measuring the magnetic field and giving that to a artificial intelligence unit. In our case, we use artificial neural networks, and the neural networks ANN is estimating the lateral and vertical misalignment. That can be easily reported to the driver, and as well as in terms of automated system, autonomous driving, it can be used for compensating for the misalignment and correcting the misalignment. The idea behind this structure is based on the magnetic field on top of the transmitter pads. On the left-hand side, we see the Y component, lateral component of the magnetic field on top of the transmitter pad. And here is the width of the pad, and this is the length of the pad. At any position on top of the transmitter pad, we have this 2D view I'm showing on the right-hand side. When a sensor is moving along the pad, it will measure a specific magnetic field. By just sampling those magnetic fields, the neural network is able to predict the lateral and vertical misalignment. To test this idea, we put 3 magnetic sensors that I'm showing in this test setup on an aluminum plate being pushed by an RC car. For easier test, we put our receiver side under and our transmitter pad over that, and we flip the transmitter pad. It's just for easier test, but it does not change the concept. Then we did, we implemented this idea, and this figure that you see on the left-hand side, on this highlighted window, it is where we are seeing the sensor measurements when they go under this transmitter pad. And each sensor is measuring its own magnetic field because they are located at different positions. And based on these values that it's reading, the neural network is able to predict the lateral misalignment and vertical misalignment in real time. I'm showing here the lateral misalignment with this red curve here. And here it is showing the lateral misalignment in real time, and the x-axis is time. Our actual lateral misalignment was 15 centimeter, and here we are estimating 14.83 centimeter after average. On this next test, I'm showing the vertical misalignment. Again, for a different test, lateral misalignment was 0 centimeter, vertical misalignment was 19.5 centimeter. And here you see that we are measuring 19.69, and the sensors are measuring something else because the lateral misalignment is different, vertical misalignment is different. How do we integrate this system with WPT? Here on the left-hand side, I'm showing that how when the receiver pad, because receiver pad and the sensing coils are located at 2 different positions of the vehicle. One is at the front, under the front bumper, one at the center of the vehicle. When the receiver pad is under this green pad, over in this green pad, and it's receiving power, the sensing coils are on top of the next pad, the red pad. And so with that condition, once one pad is transferring power, the other pad is transferring is used for misalignment estimation. With this, we are using a different frequency for misalignment estimation so that we didn't want to have any interference between 2 consecutive pads. I'm showing on the right-hand side how the idea would work. The transmitter coil, this red coil, go through 2 frequencies, 4.3 kilohertz when the first pad is transferring power. It is energized with 4.3 kilohertz. It's a sample frequency. It can be other frequencies. And when the vehicle reaches to the position of the second pad, it will go to 85 kilohertz to transfer power. Here on the left-hand side, I'm showing that how this idea is implemented with while 2 pads are implementing this idea. We are having full power transfer. There are 2 pads, and you have seamless transition between 2 pads. But this is the track current of the second pad going through 4 kilohertz, 85 kilohertz, and the inverter voltage, the same inverter that is used for power transfer, that same inverter used for misalignment estimation. We can go from 4 kilohertz to 85 kilohertz in less than 5 milliseconds. This time is more than enough for us to, for the actual system with the pads in the length of 1 to 3 meters. With these discussion about these projects that we finished at Utah State University, Dr. Pandey will discuss about our current work at NC State University and FREEDM Research Center. Dr. Pandey, please.
So actually, Reza, before Dr. Pandey, before you get started, there was a question in the chat that's related to efficiency. So with this misalignment estimation, you're relying on sensors. Earlier, when you were describing the sensorless process, is there some, have you looked at efficiency differences between these 2 methods?
So one was for misalignment estimation, and those sensors are not related to power transfer. They are just for misalignment estimation. Power transfer can be done with and without these sensing coils, but when you have for example, completely aligned system, you can easily get an efficiency about 90%. But as the efficiency, as you have like, let's say 6 to 10 centimeter misalignment, your efficiency from 90% goes down to 85%. But as the misalignment goes over, for example, 10 centimeter, you cannot transfer full power of 30 kilowatt anymore.
Okay. And that initial current where the coils overlap, you've got an initial current, like say, for example, in the first coil until the mutual inductance align. Is there some efficiency loss there?
Yes, true. If you look at what I'm showing here, so if you see, I'm showing some DC link current here without having the current. So these DC link current are associated with the losses in that period, but they are very much lower than the current that losses we have during the full power operation, because this is like a much lower current than the nominal. If the nominal current is 50 amps or 75 amps in our design, that would be just 10 amps. And the power would be, I don't know, 1/5 or 20% of the losses you would have for the full power.
Okay, good. Thank you. Okay, Dr. Pantich, we'll turn it over to you now.
Thank you very much. Thank you, Dr. Tavakoli, for presenting. Let me introduce briefly myself. My name is Jacob Pantich, and I'm Associate Professor at North Carolina State, Department of Electrical and Computer Engineering. I'm working in the area of wireless power transfer for more than 10 years. I spent 5 years as assistant professor at Utah State University, and currently I'm associate professor at North Carolina State. Some of these projects and some other projects were projects I was leading at Utah State University, and now I'm going to present some future work and current work that we are conducting at North Carolina State. First of all, I will start with our interest in wireless power transfer for personal mobility and power wheelchair and electric scooter particularly. So to motivate the reason why you're interested in this topic, I would like to share with you some results of a survey conducting among the people with disabilities who are wheelchair users and users of power electric wheelchairs. So they were asked to select among different, I think more than 10 futuristic transportation and mobility inventions. And to my biggest surprise, they actually selected new energy source. It's a 34% wanted to have a new energy source. Why that is interesting? Because for researchers and the energy source is something very common, but obviously for people with disability whose mobility and sometimes even life depends on energy stored in their wheelchairs, that's actually a very important question. So to help with that problem, we worked on a project funded by the Department of Health and Human Services, where we developed 2 generations of wireless power transfer chargers for electric wheelchairs. You see the photo of one of these generations. Let me see if I can take cursor. But Reza is showing now, that's actually the result of our first generations. First generation was intended for 250 watts. The second generation was charging electric wheelchairs inside of 2 hours using 1 kilowatt power. As you can see, we adopted a floor mat concept when wireless power transfer has been integrated inside the floor mat, power from the wall unit, and we allowed a lot of autonomy and free positioning of the wheelchair over that floor mat. That was the part of the research, but I like to share something else that people with disability who are power wheelchair users, what they face. They face a lack of public charging infrastructure. When they leave their home, it's very difficult to find a place that will be compatible with their chargers. And just to share with you some numbers, we have 1.1 million electric vehicles in the US, and we have over 22,000 public charging spots as of September 2019. At the same time, we have 1.7 personal mobility devices in the US, including power wheelchairs and electric scooters, and only 17 public charging spots. And these public charging spots are actually installed by this gentleman you see in the photo, Mr. Umbacher, who is actually in our advisory board for the project. So to resolve this problem with the public charging of power wheelchairs, we applied and we got funded recently from Department of Health and Human Services to develop a public charging infrastructure that also includes a cyber information network and associated software and mobile applications. And that project will use Chapel Hill as a testing site, and it's a collaboration between North Carolina State and University of North Carolina. Reza, could you please move to the next slide? Next area of interest for our group here is underwater charging system. Establishing connection underwater is a very challenging task. And you see some examples of some products that are capable of doing so. Lead technology at this moment is a VetMed connector. That's actually a system that is used underwater to establish contact, but it's also considered by many researchers the weakest part of underwater energy system. And that the reliability is limited due to variation of pressure. And the second challenge of VetMed connectors is how to establish connection physically. So today we use divers, or we use sophisticated remote operated vehicles to establish that connection. And both of these solutions are relatively expensive and complicated. When we talk about charging underwater vehicles, autonomous underwater vehicles, these vehicles are very autonomous. Their technology is developing every year. However, we still have a problem how to replenish the batteries that they use. And the only very reliable method so far is to practically surface those vehicles, bring them to a ship, and then replace the battery and submerge them again. There are some attempts, recent attempts, to actually provide an underwater charging system. For example, some latching techniques, and you see here one of the results you can find in the literature that is related to underwater charging of an AUV, where we use, when the researchers use a cone and a tube, and practically AUV enters that tube, and then when it's actually in that semi-locked position, we actually transfer power to that. Department of Energy is exploring new methods based on loosely coupled coils and near field resonance. You see the photo of that method, the sketch of that method. But of course, if we involve wireless power transfer in this way, there will be a challenge to overcome that layer of the water between the coils, especially in when the salinity is high. That water is very conductive and is going to generate a lot of loss. The second problem we face is, of course, alignment issue, especially in shallow waters. When the water currents are strong, it's difficult to maintain the same alignment position between two systems. In our lab, we are working on a system that is sort of middle ground between a conductive charger and this free wireless system proposed by the Department of Defense. And while developing, and we expect some good results very soon to happen. I would like to move to the next slide. Thank you. One big challenge for wireless power transfer system, dynamic wireless power transfer system, is how to bridge the gap between WPT bench, when it can, or a laboratory, or even some small outdoor test site, to macro scale outdoor testing and implementation. It's difficult to show up with a laboratory setup to legislators and funding agencies and say, hey, let's invest millions of dollars to develop a road that will use dynamic wireless charge. So that gaps really exist, and you see a few examples from Oak Ridge for Qualcomm, and some examples from our lab. Those are test sites that this enormous effort of the researchers to develop these sites, but still I could say that the reach of this research and experiments is limited. First of all, these laboratory prototypes and test sites are relatively expensive. Some our calculation shows that they go up to $4,000 per meter or $7,000 per pad, including all electronics and wireless power transfer system. Even if they are long, for example, 50 meters, they will still allow less than 5 seconds of operation, which sometimes is not enough to explore some important characteristics. Thermal characteristic is difficult to explore because they require continuous operation. We have limited repeatability. If we are talking about outdoor tests, it's very difficult to repeat the experiments and see the effect of some changes. Of course, limited speed range when you talk about indoor tests, even if we talk about outdoor tests, it's difficult to develop speeds of 50, 60 miles, 70 miles per hour. In order to actually resolve this problem, we need to follow the ideas that are presented with other industries. For example, airplane industry has the same problem. It's very difficult to test an airplane. So you need to have simulators, you need to have emulators, you need to have a complex system that can actually test these systems for hours of operation in the laboratory. And that's why what we are working now is a test station that will be at the final phase connected with a simulator, driving simulator that we have here at NC State, and that will allow hours of testing of dynamic charging systems, and also testing different conditions, different misalignments, and all other conditions. Yes, and finally, I would like to mention the project that is funded by Power America, where we are exploring high-frequency power converters for wireless power transfer. When we talk about high-frequency wireless power transfer, definitely the forerunner of that is actually Class C power converters and its derivative Class EF2, Class EF5, and some other classes. But we shouldn't forget that these converters are, when they are invented in 1960s, 70s, they were intended for constant load applications, because the load is the part of the resonance circuit that is carefully tuned to maintain efficient operation of single switch or multiple switches included in those converters. So wireless power transfer recognize the potential of Class C converters because they're very, very simple and can operate at high frequency, not to mention using gallium nitride wide bandgap devices that can actually further extend the frequency range and operation. However, wireless power transfer cannot guarantee constant load. When I say constant load, I mean constant resistance as well as constant variable reactance of the load. And that happens because of the load variation, but also because of the variation of the gap between primary and secondary. There are different methods and new technologies, new topologies developed so far trying to resolve that issue. And we can actually divide those methods to passive and active compensation methods. The researchers develop new topologies of these converters, including more elements, but still there is an open field to improve these results, especially considering that these results are sometimes complex, especially when you talk about active tuning systems. They are sensitive to tuning of the elements. Sometimes they lack a close-forward tuning algorithm, so it's really difficult to understand how to tune that algorithm. And sometimes they are, and often they do not include nonlinear phenomena like such as nonlinear parasitic capacitance of the switch itself. So we are working in this project trying to explore different nonlinear techniques that will be combined with gallium nitride devices that will be able to provide a passive compensation while still actually allowing much wider range of load that can be applied to this converter. That's about the projects. Now I'm gonna use a few minutes to talk about how we see here in my research group, how we see a future development of wireless power transfer. This is just one attempt. I would like to share some thoughts and some classification that we usually use in our group. So first of all, I would like to talk about future and current WPT applications. First of all, we can recognize not that large group of applications where the wireless power transfer plays a key role. That's actually key technology, in a sense that that technology defines the space and scope of entire application. And I listed some of them where I believe that wireless power transfer really determines how the other parts of the system will operate, determines how large, for example, the system is. The second technology, the second application of wireless power transfer, and that application is growing every day. That application is where the wireless power transfer is there to support autonomy of different devices and vehicles. And that's a very broad category of applications, and I'm including here some of them: unmanned aerial vehicles, personal transportation, and dynamic electric vehicle charging. So let me use the let me use the example of UAVs and explain how important wireless power transfer can be in those applications. So UAVs are very intelligent devices. They have a lot of processing power, excellent cameras. They have communication devices, but excellent control algorithms that controls flying. But they struggle with the energy. And after 30 to 40 minutes of flying, we need to land them to replace the battery, and they take off again and do their mission. So obviously their autonomy is completely limited by limited energy, onboard energy sources. So wireless power transfer can really be the last, cutting the last cord and practically allowing this system to be autonomous if we actually develop wireless charging, autonomous wireless charging system. And the final category is where the wireless charging actually supports the operation of the other systems, providing convenience, improving convenience of these devices. And I've included here cell phone chargers, consumer electronics, even static electric vehicle chargers is just a matter of convenience. It doesn't really bring some critical issues that will alter the operation of electric vehicle, for example. Based on these three categories, I kind of see that different approaches needs to be taken when designing wireless power transfer system. So there are different design objectives. In the first category, where the system is determined by wireless power transfer system, is WPT needs to be optimized. And that's actually challenging system for wireless power transfer engineers to do their best work to get the maximum power transfer to biomedical implants, or to have a very efficient mobile factory automation that is based on WPT or something else. In the second category, wireless power transfer system should be designed to support autonomy. But what is even more important and sometimes somehow neglected is that wireless power transfer system should expect and use the help of intelligence and autonomy installed on the device. So with the help of that autonomy, for example, we can solve a lot of wireless power transfer system issues. For example, alignment, foreign object detection, cyber safety, communication, everything, for example, of that exists already at an AUV, and we can use it in our WPT system. So in other words, autonomous researchers and designers of autonomous system should work hand in hand with WPT researchers and engineers to build a system that works best for both worlds. And finally, we talk about the third category, convenience. We need to focus on improving convenience. We are somehow serving that system, and we need to focus on efficient time utilization. For example, we need to focus on portability, and we need to avoid any unpleasant situation that charging system can use, for example, you have a charging platform, you put the two cell phones, and when you put the second cell phone, the system stops working. That's what we want to avoid, and our system needs to be designed in that direction to improve and maximize the convenience that system provides. Based on these three kind of directions, future applications, I kind of identified some critical research challenges and directions in the future, and intentionally I put standardization. Standardization is very important, and it took almost 10 years to develop first standards for electric vehicles, and the CHI standard and Air Fuel Alliance standard also exist for low power devices. And that's a very important topic, because that allows industry members to enter this area and participate actively in developing, selling, and improving wireless power transfer system. Next question is, of course, getting more power from wireless charging systems using modular or even single unit designs. Then, as I already talked about, the integration between intelligence and automation with the wireless power transfer system, which can solve a lot of problems that we wireless power transfer designers now trying to solve, which may not be necessary. Then, of course, grid integration. One problem that is typically neglected is power metering. How are we going to measure the power we deliver, for example, to an electric vehicle? The only fair way to measure is to measure the power that goes through air gap, but that's very, very difficult. So we measure power on the primary, measure the secondary, and always somebody is charged more in that case. We expect new advance in material design, including magnetic materials, wires, testing procedure, as I mentioned, and test beds are very important. And we have some test beds for stationary charging system. We expect more, of course, test beds for dynamic charging system in the future. We need to work closely with mechanical engineers. We need to work with civil engineers to derive a close procedure, exact procedure how to install these devices inside the road, and to guarantee, for example, when you install the dynamic charging system in a highway, you need to guarantee 20 years of operation. And when you mention to civil engineers to put something in the road, they are very skeptic and they are very worried how it's going to work in the long run. And of course, everything is about the economy and financial side, and we need more exact evaluations of capabilities and closing financial construction for example, some large projects related to dynamic charging. These are, and at the end, I would like to mention some agencies and centers that supported our research, including FREEDM System Research Center, then Department of Energy Power America Program, Department of Health and Human Services, Toyota Motor Corporation, Toyota Research Institute of North America, and Select Research Center at Utah State University. Thank you very much. We are open for your questions. Myself and Dr. Tavakoli will try to answer. If we cannot answer some of these questions, feel free to contact us, and we are open for any collaboration in the future. So feel free to contact us if you have some ideas how our work can be advanced, or how we can actually combine our research efforts. Thank you very much.
Thank you, Dr. Pantic and Dr. Tavakoli. Appreciate the presentation. We do have a couple of questions that were put in the chat. This relates to Reza, your presentation. So in the dynamic wireless power transfer systems, which type of compensation system is good, and what type of receiver pad power conditioner will be the optimal choice? And you're muted, Reza. Reza, you're muted.
Excuse me about that. So I was saying that there is no solid answer to that, but what we use was LCC compensation, and we think up to a medium power, like 30 kilowatt, 50 kilowatt LCC and double LCC would be good, but going more than 50 kilowatt, probably series compensation would be the compensation to go for. In terms of power conditioner at the receiver side, again, for the bus project, we use the buck converter, but it depends on your design. But People have used buck boost, and boost, but what we use was buck. And again, it depends on the system and the details of how the system is designed.
Okay. One final question. Looks like we're right at noon right here. Several people have asked if we could share the slides, and I assume that's okay.
Yeah, I think so, yes.
Okay. I see both of you nodding.
Yes, I think it's okay. Yeah, we can share slides.
Okay, good. So we will send the slides to the attendees, and we're right at noon here. If anyone still has questions that were unanswered, feel free to email us. Our contact information is on the Freedom System website, and like we said, the recording of this presentation will be available on the North Carolina State Electrical and Computer Engineering YouTube channel, which you can find just through a Google search. It'll show up in a couple of days. Thanks a lot for attending, and I hope everybody enjoys the rest of their day.
Thank you.
Thank you.